Thank you for the introduction and for the chance to speak here. It's a great pleasure and honor to be able to speak at the Simon's lectures. Actually, earlier this semester, I was participating in a special semester at the Simons Institute on the other side of the United States. And the theme of that special semester is geometry of polynomials. And when I arrived there and met people, I was surprised to learn that none of them were algebraic geometers. So you can run a special semester titled Geometry of Polynomials with very little algebraic geometers involved. I thought algebraic geometers had copyright to that term or something, but apparently not. But I'm going to tell you about my work with Peter Brandon, which clearly belongs to the topic of geometry of polynomials in that sense of the word. But our work, at least from my point of view, is inspired by algebraic geometries. Geometry of polynomials inspired by algebraic geometry. But none of the statements and technicalities appearing in the proof actually use algebraic geometry, so you can ponder about the actual technical connection. So the part that was most surprising to me when I was working on this project was that algebraic geometric mindset or point of view can be actually useful in not only in finding interesting statements to prove on elementary or old school analysis of polynomials, but also it's also useful in finding the proof. So all the proofs of the statements that I'm going to show you, actually I and Peter are modeling on the hypothetical geometric situation, and it makes the argument flow very smoothly. So this is where I'm coming from. So let's think about a projective variety, say y living inside Pn for some n, maybe over some field. And out of this y, what I'm going to do is I'm going to compute the volume of y. Let's say when y and Pn are defined over the complex numbers, and of course I'm computing y with respect to the metric given to me by the metric on Pn. So I'll get a number, the volume or the degree of y, but that number will very much depend not only on y, but also on how it sits inside Pn. And then algebraic geometers consider the behavior of this function on the space of all possible projective embeddings. There are many, many different ways you can put y inside some Pn for varying n. And this is an enormous infinite set. But this is not an arbitrary set, but it is a cone. They form a cone. So this, the cone of projective embeddings is of y. And the reason why I'm calling this set to be a cone is simply because of the fact that if I'm given two different embeddings of y inside Pn1 and Pn2, say, then I can produce a third embedding of y given by the embedding of the product of two projective spaces into a larger one, the standard embedding of the product of projective spaces. If you collect these all different embeddings, and for each embedding, if you consider this number, the volume or the degree of y, then it turns out that this function is a polynomial in a precise sense that I'm going to tell you shortly. And not just any polynomial, a very special kind of polynomial. Because the behavior of the volume function is controlled by the Hodge theory of y. And Hodge theory of y, among other things, says that log of volume function is concave on this cone. So technically speaking, this is what I have in mind. So let's think of list of variables, W1 to Wn. This W will going to be the variables of my polynomial. And maybe I have list of n different embeddings. So for example, maybe I'm thinking of one way of embedding y into projective space, and maybe some other way of embedding y into projective space, h1 and h2, in which case I will have two variable polynomial. And the polynomial that depends on y and the list h in variables w that I have in mind is the volume of y with respect to the embedding given by the sum, which makes sense, for example, when all the wi's are positive integers, because you can add two projective embeddings. And it turns out that this is indeed a polynomial function. If you think about this situation, it's completely natural to algebraic geometers to consider the limits, because this polynomial is not a single polynomial, because it comes in families. Because you can vary h, the list h, inside that cone. In particular, you can consider the question of what kind of polynomials do you get when you drag each one of the hi's to the boundary of this cone. So this cone is, in a precise sense, an open cone. So it does not contain its boundary element. So if you have a sequence of projective embeddings, and there is something that you wish to call it its limit, and it often does not correspond to any embedding, but only a map from y, contracting maybe interesting subvarieties and so on. And this is one way of getting into the definition of Lorentzian polynomials. So in my mind, I secretly always think about Lorentzian polynomials as those polynomials that appear when I drag each one of the hi's near the limit of this cone of projective embeddings. But of course, I should also again emphasize that entire theory that I'm going to present today has nothing to do with this particular situation, probably. But the one thing that was most amusing when I was working on this analytic theory of Lorentzian polynomials with Pater was that it connects two different notions of convexity in a very natural way. That of continuous convexity and discrete convexity. And these two different notions of convexity are related to two different ways how you can view a polynomial as a function. Of course, I mean, almost all the people, except very few algebraists maybe, think of polynomial as a function. Maybe I have n variables, and we are looking at a special kind of function from Rn to R. And of course, this function is given by evaluating f at a given point w. That's one way of viewing polynomial as a function. But there is, of course, equally natural way of viewing polynomial as a function whose domain is n to the n. So the non-negative lattice points in n dimensions, where the function is obtained by taking the alpha coefficient of f, where I identify n to the n with a set of monomials in n variables. Of course, it is natural to go back and forth between this description and that description, of course. And say, for example, when f is homogeneous, which will always be the case in my situation, you get this function from that function by taking the partial derivatives partial alpha, and you get these functions. And when you know the coefficients, you can assemble them into a polynomial expression, which combinatorialists call generating function or partition function. I want to add one of my standing conventions that whenever I talk about generating functions, I'm always going to mean what is sometimes called the exponential generating function, which means that I'll always write f as a sum of terms, C alpha, where the monomial is w to the alpha divided by alpha factorial, and I'm summing over alpha. So whenever I talk about coefficients of f, I'm talking about this C alpha, where alpha will always be the list alpha 1 to alpha n, and w will be the list of variables w1 to wn, so that w alpha, sorry, let's do it this way, so that w alpha will be the product w1 to the alpha 1 dot 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 wn to the alpha n, and alpha factorial is the product of the factorials of the alpha i's. So everybody who loves polynomials have wondered questions of the type, how do the function theoretic properties of this function is related to that of this description, and so on. And the beauty of this, what I found beautiful about Lorentzian polynomial is that this property of being Lorentzian can be naturally interpreted in both worlds, and somehow it connects this description to that description from the point of view of convexity. So let me start by defining basic objects that I'm going to study. So throughout, I'm going to write h dn for the set of homogeneous polynomials of degree d in n variables with coefficients in real numbers. So this is a finite dimensional real vector space given d and n. And let me start defining subsets, interesting subsets of that. starting from the case when d equals 2. So the case of quadratic forms. So L naught of a 2n will going to be the set of quadratic forms with positive coefficients that have the Lorentzian signature plus, minus, minus, dot, 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 minus. So exactly one positive eigenvalue and non-singular. Because I'm requiring all the coefficients of the quadratic form to be positive, and I'm putting an additional open condition here, I have actually defined an open subset of H2n. And when d is greater than 2, I'm going to denote L naught dn to be the space of strictly Lorentzian polynomials. By which I mean those polynomials that are homogeneous of degree d in n variables with the property that the ith partial derivative of f is strictly Lorentzian of degree d minus 1 for every index I in n. So the only actual condition is imposed on the quadratic polynomials, because if you're given f and want to check the inclusion in this space, you have to check that every one of partials is in the space of strictly Lorentzian polynomials. But how do you check that? You again check partials and so on until the degree becomes 2. And there, if the quadratic form is non-singular and have exactly one positive eigenvalue, then you have a strictly Lorentzian polynomial. So this is an open subset of HDN. And you can define Lorentzian polynomials in many different ways, and that's the point of the talk. But let's take this as an official definition of Lorentzian polynomials. Those polynomials that you can get as limits of strictly Lorentzian polynomials. So these two are definitions. So I have defined an open subset of, let's say, P of HDN. And to me, Lorentzian polynomial is those polynomials that appears in the closure. I have drawn this a little bit of wobbly picture to emphasize that this is not a convex set. If you add two Lorentzian polynomials, in general, you don't get a Lorentzian polynomial. Sometimes you get a Lorentzian polynomial, and this is a delicate condition to decide which is what is what case. Mainly because this is a signature condition that's imposed on quadratics. It's not additive. So here's a maybe non-example. So let's consider this polynomial, a cubic polynomial in two variables. Sum of cubes. let's take the partial derivative. Partial 1f, that would be 3w1 square, and partial 2f equal 3w2 square. And let's ask whether the partials are Lorentzian. They are clearly Lorentzian because they are limits of the type, maybe I have an epsilon to the 10 here and w to the square. If my epsilon is a small positive number, then I have a strictly Lorentzian quadratic form. So this is a 2 by 2 matrix with diagonal entries 3 and epsilon to the 10, and off diagonal entries epsilon and epsilon. So the determinant must be negative, so it has a mixed signature. In particular, it has a Lorentzian signature. And same for this. So these two are Lorentzian. But interestingly, I claim that this is not Lorentzian. So even though you can approximate each one of the partials by strictly Lorentzian polynomials, you cannot approximate the original polynomial. So in this, f is somewhere far out here. Let me also show you some easy examples of polynomials that are Lorentzian. So this is sometimes called Newton's inequality for real-rooted polynomials. And Newton's inequality says that in our language, the product of D linear forms, maybe I have AK, W2, for some positive numbers or non-negative numbers AK, is Lorentzian. The usual statement of the Newton's inequality says that a univariate polynomial, all of whose roots are negative real numbers, have ultra log concave sequence of coefficients, which translates to the Lorentzian property in the bivariate homogeneous case. So in fact, and you notice that this, for n equals 2 and arbitrary d, this already covers the full dimensional part of this set that we are interested in. So the interior is P of L naught of a dn, and we have the closure. So in fact, especially for Pater, the desire to construct the theory of Lorentzian polynomials comes from this example, because there is a well-developed and very interesting notion of stability of polynomials that generalize the notion of real rootedness to case of many variables. And it turns out that any homogeneous stable polynomial is Lorentzian. So one of the things that I first want to do is to give a simple characterization of this closure, or the set of Lorentzian polynomials. And essentially, that simple example that you see up in that board is the crucial one. If you generalize it into higher dimensions in the right way. So the right notion to look at is provided by discrete convex analysis in the sense of Murata, which provides a definition of a convex set, among other things, for a subset of n to the n. So the definition that I'm going to tell you shortly is a little bit technical, and in particular, it contains more than 2 quantifiers. So you may be a little bit confused if you've never seen before. But I want to emphasize that this is really correct and hard-earned definition. Not just Murata's work, but building up on many people's work, including starting from Whitney and Lovash, and maybe Edmonds, and person most relevant to this crowd may be the work of Postnikov and many others, who produced many different theorems over many decades to justify that what I'm going to propose here is the right notion of convexity for discrete sets. So, Murata defines a subset J of n to the n to be M convex if the following condition is satisfied. So for every 2 members, alpha and beta, in the set J, and any index I, one of those n coordinates, satisfying alpha I bigger than beta I. Remember that this is the ith component of I, alpha. The condition is you want J in n where alpha j is smaller than beta j, such that alpha minus ei plus ej is in J, and also beta minus ej plus ei is in J. So this condition is called the symmetric exchange axiom. And for those of you who know make choice may recognize this condition. But before that, let me show you some of the convex sets, examples of convex sets in this sense of the word. The picture that you want to have in mind is maybe this. You have this EI direction and EJ direction, by which I mean ith standard unit vector in n to the n. And maybe you have 2 points, beta and alpha. And essentially, what you want is when you drag beta toward alpha and drag alpha toward beta, you want both of these new points to be also in J. And the crucial difference with the usual continuous notion of convexity is that these two EI minus EJ directions need not align with the direction that connects alpha and beta. So there can be a small disalignment, except in the case when alpha and beta are in the edge of the convex hull of J in the usual sense of the word. In that case, the condition forces these 2 points to align in EI minus EJ direction, which is one of the roots in type A root system. So one popular way of getting a convex set is to start from a connected graph on n edges. So it's the same n, and take J to be the set of spanning trees of G, viewed as a collection of edges of G. And the entire collection is viewed as the collection of 0, 1 vectors in n to the n. Then this is a convex set in the sense of discrete convex analysis. The claim is that if you're given 2 spanning trees, different spanning trees, and pick any one of the edges in one spanning tree, not in the second spanning tree, you can always find an edge in the second spanning tree, not in the first spanning tree, so that exchanging these edges produce 2 new spanning trees. And closely related example would be to start with n vectors in some vector space over field F of dimension D, and take J to be the basis of the vector space in A. Again, viewed as a collection of 0, 1 vectors in n to the n. And these two are actually examples of matroids on n. And one way to define what matroid is to simply declare that these are M convex sets of 0, 1 vectors in n to the n. And in this language, people usually call the matroid set or M convex sets arising from the second example, called the collection of vectors, called matroids representable over F for a field F. So here's the second part of the definition that I need to state the result. So let's call M the n for the space of homogeneous degree D polynomials whose support of F, which I mean the set of monomials appearing in the expression for F, is M convex. And similar to before, I'm going to start defining things for the quadratic case. So L2n will be the space of quadratic forms with non-negative coefficients that have at most one positive eigenvalue. So compare this with the definition of L not 2n that's over there. So it's clear that if you take the closure of L not 2n, so the space of Lorentzian quadratic forms, is contained in L2n. And in fact, it's not too hard to show that this is actually the closure. This is the space of Lorentzian quadratic forms. So we know what the Lorentzian forms are when d equals 2. And the examples of this kind shows the subtleties that may appear for higher d's. So when d is larger than 2, let's say that LDN is by definition the space of polynomials in MDN, so whose support is M convex, with the property that the ith partial derivative of f is in L to the d minus 1 to the n for all I. Again, this is not really a recursive definition in any sense. So it turns out that if f has M convex support, then each one of the partial must have M convex support. So in addition to the M convexity of the support of the original f, the only thing that's imposed here is the signature condition on the quadratics that you obtain.
So these two examples are all matroids. What are good examples of non-matroids that we should think of as discrete convex?
Maybe Newton's. So take any real-rooted polynomial, and I claim that these are Lorentzian.
Any that come from combinatorics that's not from polynomials?
Yeah, all these example matroids are 0, 1 vectors. So in terms of polynomials, these are special polynomials which are degree 1 in each one of the variables. Of course, there are many variables, many polynomials out there which are not square-free. And we're going to see some of those naturally occurring examples later. And the theorem is that LDN is the closure of L naught dn. So there are actually two assertions hidden in this equality. And both directions are, I think, non-trivial. The first thing is that if you can obtain a polynomial as a limit of strictly Lorentzian polynomial, then its support must be M convex. That's one direction. And the other direction is that if you have a polynomial whose support is M convex, and all the symmetric matrices that you obtain from it has the correct signature, then you can actually globally limit the polynomial by strictly Lorentzian polynomials. So strictly Lorentzian polynomial, by definition, has the full support. Every monomial of degree d must appear because I have declared that all the coefficients must be positive. So the study of Lorentzian polynomial is that when I take the limit of those kind of polynomials, what kind of monomials can I delete without destroying the signature condition? And the condition that you want is that of M convexity. Actually, you can. So in particular, this LDN, defined in that way, is a closed set, which is very strange if you stare at the definition. Because this MDN, the condition on the support, is definitely not a closed condition nor an open condition. It's not anything. It's just a form of the support. But the way it interplays with the signature condition forces the set to be closed. So if you look things inside the projectivization, you see a compact set because it's closed. But not just that. It turns out that this is a contractible set, although not convex. So this, I tend to view this as a shadow of this, the feature that preserves some properties of convex analysis in the usual sense of the word. Subset of the projective space HDN. And not only that, it has, of course, the contractible interior, which is P of L naught of Dn. So this is almost like a ball. I have not thought about carefully whether it's actually a ball, but to my mind, this is, let me pretend that this is a ball. And of course, you can write this object naturally as a disjoint union, where the disjoint union is over J, where Lj is by definition Lorentzian, whose support is J. And the statement continues. You can even say something about those pieces Lj. And the first thing that you notice that Lj is non-empty. In other words, there is a Lorentzian polynomial with support J if and only if J is M convex. So the disjoint union is actually over all M convex sets for that fixed D and N. And in this case, this little piece that you see in the boundary, deformation retracts to a distinguished point, say f of a j, which is, of course, the generating polynomial for j. So let me try to recap what just happened. So I started by defining this open subset of a projective space A. And the conditions defining this open subset is entirely analytic in nature. I've simply declared that all the coefficients should be positive, and then I have imposed some non-singular signature condition on the quadratics. So in particular, there was almost nothing combinatorial about it. It's an entirely analytic condition or smooth condition. But once you take the closure of this ball-like object, then in the boundary, you notice that the boundary comes in pieces, these little LJs. And each piece is also ball-like. So there is one distinguished point for every one of the convex subsets of n to the n, to which each piece deformation retracts to. So each piece in this sense is also ball-like. And the way, so first of all, individual combinatorial objects that you see in the boundary are very intricate, and the way they meet each other is also quite intricate. So it's like a soccer ball where the interior has absolutely no combinatorial structure. But on the boundary, you see some interesting discrete geometry, and the pieces of which, each of which are ball-like, meet each other in an interesting way. So on the single ball-like object, you see like many of your favorite objects, like many of these different graphs, or some of your favorite vector configurations, maybe over field with 2 elements, or characteristic 0. So these two pieces are adjacent to each other, because if you think of the configuration of 7 points or 7 vectors in 3 space, then the Lorentzian polynomials corresponding to this one has exactly one more term than the Lorentzian polynomial corresponding to this one, simply by taking this coefficient approaching to 0. And same for these spanning trees of these graphs, where you have one less variable and many less spanning trees, so on. But other than the satisfaction that you get by staring at balls, you get some actually useful analytic properties from this combinatorics. Analytic properties. So in particular, you can show that these properties are equivalent for any homogeneous polynomial f with non-negative coefficients in n variables. First is that f is Lorentzian. And the second is that f is strongly log concave, whose definition, due to Leibniz Gurvitz, goes as follows. So for any alpha in n to the n, the alpha's partial derivative of f is either identically 0 or the logarithm of the partial derivative is concave on the positive orthant. So again, I don't think any of the directions 1 to 2 or 2 to 1 is obvious. And let me try to convince you that this theorem has a content. So for example, one thing we can do with it is to show that the product of strongly log concave polynomials is strongly log concave. I mean, it feels like that the statement of this kind should be either false, or if it's true, you should be able to prove it by calculus or something. But apparently this was an open problem. And try to, if you still, the case n equals 2, the case of 2 variables, it was a conjecture of Pimentel, later proved by Liggett. And this proof is about 10 pages. So the case of two variables. But the point is that it's very easy to verify that the product of two Lorentzian polynomials is Lorentzian. So what you need to check for Lorentzian property is clear. You have to check the condition on the support, which is simply the statement that the Minkowski sum of two M-convex set is M-convex. And you also have to check the signature condition, which is, let me just say that it's very easy. Oh. So one thing that I learned, the principle that I'm adhering to while studying these objects is that checking log concavity of polynomials is usually very hard. So for example, if I give you a polynomial like this, our old polynomial. Let's do it this way. Maybe a quartic polynomial like this. And now if I ask you to prove or disprove that this polynomial is log concave on the positive orthant, namely on r to the 2 positive, it's quite painful to check whether the statement holds or not. In principle, what you have to do is you take the log of this, and you have to check the concavity. So you take the Hessian of this polynomial, and somehow you hope that you can maybe collect a square or something to show that determinant is always positive on the entire positive orthant or so, which is usually quite a painful thing. But checking the stronger property of strong log concavity, so the log concavity plus log concavity of all the partial derivatives, is extremely easy. In fact, you immediately notice that this is not strongly log concave because there is a hole in between. So there is a support consists of 2 points because I have two polynomials and I have a missing hole in between, which violates the M concavity. And it's also very easy to show that something is Lorentzian because you simply check that there are no holes, say in the case of two variables, which is a combinatorial thing. And you have to simply check the signatures of certain 2x2 matrices in this case, which is also very easy. So the principle is that proving the Lorentzian property of a polynomial is very easy, except when the polynomial is not Lorentzian, in which case it should be impossibly difficult. And this principle has been very, very useful. So you can formulate a bunch of combinatorial conjectures generating functions arising in combinatorics and other areas. And you simply conjecture that they are Lorentzian. And you try to prove it. When they are Lorentzian, usually the proof is surprisingly easy. And if you're having a hard time for some reason, then they're probably not Lorentzian. So this is, I think, is an extremely nice business model. So I'll trying to demonstrate some examples of this in the coming lectures by showing you some well-known polynomials are Lorentzian. Let me summarize some of the well-known ones. The volume polynomial associated to projective variety y when my H is the collection of so-called Neff divisors, which are by definition limits of projective embeddings, are all Lorentzian. And for list of convex bodies, delta 1 to delta n, say, in D space, there are n of them, the volume polynomial measuring the volume of Minkowski sum is Lorentzian. And so on. Oh. So I know that many of you are secretly planning to only attend the first lecture. So let me try to cast a wide net of keywords to keep some of the audiences for the second lecture. So there are many, many more interesting Lorentzian polynomials. And of course, if you look at that map of the space of Lorentzian polynomials, the interior is kind of dull. So all the interesting combinatorial action is happening on the boundary. It's a little bit like Australia. So it's you certainly expect to find many, many more interesting Lorentzian polynomials on the boundary. And I'll show you some of the interesting examples that I found so far with my friends. So what's coming up next is the proper introduction to discrete convex functions instead of convex sets. So I have not actually done any convex analysis properly so far, but I'm going to introduce this. And that will lead us naturally to certain considerations in this funny geometry called tropical geometry, where people call objects like this a line. And that will lead us to the Lorentzian property of Potts model partition functions that appeared in Sasha's talk. And certain extension of that consideration lead naturally to the hidden convexity properties of graph homomorphisms and graphs on surfaces. And lastly, I'll also going to talk about the connection to the representation theory of our favorite group, GLN, and sure polynomials. So if one of these keywords interests you, then maybe you will enjoy the next talk too. Thank you.
Any questions? So in those examples that you gave that are subsets of Lorentzian polynomials, let's assume for 1 second that they're proper subsets of, they're strict subsets. The question that I have is, for those, let's say stable or a volume polynomial, do we get extra structure on the support, or do we get extra structure on the signature for those strict subsets?
So if you look at this map, there are certain well-explored territories. Stable polynomials live here, and Minkowski's volume polynomial live here. And we know that this is a proper Venn diagram. So there is polynomial here, there's polynomial here, there's a polynomial here, there is a polynomial here. So this guy is related to, for example, Fano configuration, if you know what that is. Examples of this kind is related to Pappus configuration, for example, can be obtained from. And examples of this kind can be obtained from the Hesse configuration of 9 points on the elliptic curve, for example. And you can get many of these examples from graphs and their spanning trees. So I don't know what the answer to your question. Probably no. But let me just take this chance to pose a question that I forgot to mention. So this is a proper Venn diagram. But one thing that I have no idea is the class that I'm mostly interested in. So the volume polynomials of projective varieties. So my question is that could it be the case that LDN is the closure, or how would you disprove a statement like LDN is the closure of volume of YH W? Maybe let me take the projectivization up to scaling to be safe, where I vary Y over all d-dimensional projective varieties and vary H over all the NEF line bundles. So I have no idea how large this class would be. So, and whether, of course, you can make the question finer and finer, maybe varying over only over Y defined over one of your favorite fields at P bar, or whether this closure depends on the field, et cetera, et cetera. So, but I don't know a single Lorentzian polynomial which is provably not in this closure. So, but if it were, probably not, but if it were, it would be kind of amazing. So the space of all projective varieties, in a sense, of fixed dimension fits into a single ball-like object with absolutely no holes or anything. So that would be interesting.
So can I ask you two questions? So one question is more like clarification. So this notion of Lorentzian polynomial is depends on the basis, choice of basis.
That is crucial, right?
But like for degree 2, it looks like almost basis independent.
That's right. The amazing fact that you are, I think, related to what you're observing here is that if F is Lorentzian, maybe Fw, then F of A of a W, the coordinate change, is also Lorentzian whenever A is non-negative matrix. And this is looks like, again, one of those calculus type questions, but it's actually, yeah, I would say somewhat tricky to prove, but it is a remarkable fact.
Okay. And like second question is, so as you said, this boundary of this object includes realizable and non-realizable matroids.
Yeah,
So how is it related to Macphersonian?
I don't know.
Some kind of Macphersonian as a model for all.
That's right.
Yeah. Is this kind of somehow embedded into this picture? Or?
Maybe, but I don't know.
So right at the beginning you said that you inspired by some ideas from algebraic geometry. What were you referring to is this connection? I mean, you connection, but is that what you meant? Or is
That's right. So I completely forgot to mention that connection, which I emphasize so much. So for example, I mean, imagine how you would prove the implication from 1 to 2, for example. It looks like a completely absurd implication. The only condition that I've imposed here is essentially the log concavity of the quadratics that I obtained by partials. So it's a degree 2 condition. How can I get something global like this if in addition, I have this M convexity? So what I'm modeling is the well-known implication in algebraic geometry. So the log concavity of the volume polynomial of a projective variety is coming from the so-called Hodge-Riemann relations in topological degree 2. So what I'm assuming is the same signature condition, but for degree 2 polynomials instead of the original F. So and the condition that I'm imposing is essentially the Hodge index theorem for surfaces. It's surfaces because I'm looking at quadratics. And the main philosophy of the cohomological study of projective variety is that anything non-trivial cohomologically, if there is a statement, the statement can be reduced to the middle cohomology. And if you're interested in this kind of spectral condition, you only have to consider the case when the degree in question is the middle. So in which all our assertion reduces to the quadratic case. So this is like the proof of Hodge-Riemann relation in degree 2 by assuming the Hodge-Index theorem. And there is a well-known inductive framework developed by many, many people, and most recently by Cataldo and Migliorini, by reducing the full Hodge-Keller package to the same statement for smaller objects and just for finitely many of them. And the implication from 1 to 2 is exactly modeled on that.
One last question.
So perhaps a bit long-winded, but sincerely naive. Suppose you're talking to an electrical engineer from 100 years ago where people understood calculus, knew complex variables, but no formal linear algebra, but they understood network determinants and the graph theory from Kirchhoff. In that language, Hurwitz makes sense, stable polynomials make sense. We still talk about that in control theory from a century ago. And then there's Morph's, the residue theory, gets jazzed up in like Atiyah-Bott-Garding treatment of lacunas and hyperbolic PDEs and Garding polynomials. But that seems all formulas and calculus, but there is a connection there, but I don't quite see it right off.
Yeah, I mean, the graph theory statement is that the spanning tree polynomials are stable, which is another name for hyperbolicity in positive directions. So at least I could communicate with them in that language, and they probably know what these are, Minkowski's volume polynomials and mixed volumes and this isoperimetric inequalities and so on. So this is really isoperimetric inequality, so Minkowski being Lorentzian. So I can also communicate with them, and but it's extremely hard to characterize Minkowski volume polynomials. It's a well-known open problem, but I can at least tell them there is a very natural larger space on which you can develop successful theory. And I'm not sure that was the answer, but that is how I would go. Yeah.
Okay, let's thank